Today, you're going to be taking some notes, and we're going to be taking some important notes. These notes are going to go with your lab, which is going to be your major assessment for this unit. This is the thing you're doing instead of taking a test. So make sure, if you don't have the sound on, turn the sound on. Get out your headphones. This is something you really want to understand and not just copy down. So what your lab is looking at is chemical reactivity. There are a lot of different ways that I could define this, but we're going to start with a pretty basic definition of what is it? So, chemical reactivity at the most basic level is the tendency for a substance to change when exposed to stimuli. Basically, all substances are reactive. Not all substances react equally. So, for example, we're going to compare two nails. We're going to have an iron nail on the left, and we're going to have a stainless steel nail on the right. Now, iron is an element, while stainless steel is an alloy, which means it's a combination of different elements melted and mixed together. That doesn't really matter. For our purposes, we are comparing two different metals. The fact that they're nails doesn't really matter. Nails are just something easy to draw. So we're going to take two samples and expose them to the same stimuli. We're going to leave them outside, which means they're going to be exposed to air containing oxygen or O2, as well as water. Given the same stimuli, we are not going to see the same outcome. If we left an iron nail, raw iron nail outside in the rain, in the wind, in the air, most of you know what's going to happen to it. It is going to disintegrate into a rust pile. Rust being our everyday word for oxidized iron. But what we really care about is it changed. It changed significantly. It underwent a chemical reaction. Now, the stainless steel nail left outside in the same conditions for the same amount of time is going to have a different outcome. That stainless steel nail gonna be relatively fine. Now, it might change a little bit. You might get like a speck of imperfection on there, but we can definitely see this iron nail reacted much more strongly and quickly than that stainless steel nail. Now, in your lab, you're not going to be comparing nails, but you are going to be comparing metals. You're going to be looking at 5 different metals, and instead of exposing them to air and water, you're going to be exposing them to 5 different chemicals. And you're going to see which metals react readily, which metals react not so readily. When you do that, what you are doing is investigating something called the reactivity series. The reactivity series is a ranking of elements. Traditionally, they are going to be all metals based on their tendency to react. Some elements are going to be very, very reactive, and we would see them near the top of the series. Which means they react with a ton of things. While other elements are going to be non-reactive or unreactive, and we see them at the bottom of the series. So, some examples of highly reactive elements. These are elements that react with things just like normal water. Would be elements like potassium and sodium. Other elements might not react readily with water, but might react with water if you left them in there for an extended period of time, or they might react with other chemicals such as weak acids. Those would be elements like calcium. And then farther down the list, we get relatively stable metals. So they might only react with moderate acids or other chemicals with a moderate strength. And these are going to be a lot of the transition metals like tin. And then unreactive elements, it takes a lot to get them to change. You might need something like an exceptionally strong acid. And these are going to be things that you think of with precious metals. So things like gold and platinum. In general, the highly reactive metals are going to change easily and quickly. When exposed to a stimuli. The unreactive metals are very resistant to change. Your task in lab is to investigate the metals that I give you and create your own ranking. Which of the 5 that you have are most reactive? Which of the 5 that you have are the most unreactive? Now, chemical reactivity is something that we can predict. Highly reactive elements tend to have things in common. Non-reactive elements, non-reactive elements tend to have things in common with each other as well. So when we are predicting reactivity, what we are going to be looking at is electron arrangement. Highly reactive elements are going to be elements with valent shells that are nearly full. Or elements, actually, I shouldn't say that they're nearly full. I should say that they are close to a full valence shell. Now, since we're looking at metals, we are looking predominantly at the left half of the table. If you remember the periodic table, split into our three categories along this diagonal. The metals are found on the left and the lower right. The metalloids are found on the diagonal. We'll stripe them, checker them. And the non-metals I'll color in are found on the right. And hydrogen. Now, given where the metals are located and the fact that elements are most reactive when they're close to a full valent shell, that's going to mean reactivity increases towards the left. Because elements on the left are closer to reaching that full shell. For example, elements in column 1 are only 1 electron away from a full shell. They really, really, really want to give that electron away. They give that electron away in chemical reactions. Elements in column 2 also pretty close to a full shell. They are readily able to give that electron away, so they are going to react fairly quickly. Now, that gives us a row trend, more reactive towards the left. Elements are also more reactive, or specifically metals, when they have more rings or shells. Which means metals are going to be more reactive on the left, specifically on the lower left. And we'll learn more about this as we start getting into some sample problems. But these are our rules for reactivity. This is an overview of what the reactivity series is. And this is a diagram to help you understand what we're looking for in lab. What are we looking for? We're looking for metals that change. We're looking for how easily they undergo that change. Now, we're going to do 2 practice problems applying the rules that I just gave you. So, for example 1, I want us to predict reactivity. We are going to compare strontium versus antimony. Not antimony, because I want to do a metal. Tin. Which would you expect to be more reactive and why? First thing we've got to do is find these on the table and figure out how they differ. So on our periodic table, strontium is right here. Row 5, column 2. Tin, also in row 5, but now tin is in column 4. So our difference here is going to be in our valence electron number. Strontium has 2, while tin has 4. Strontium is only 2 electrons away from a full shell. All it needs to do is give away 2. And then it reacts and forms an ion. While as tin is 4 electrons away from a full shell. It's got more to move. Now, technically it could gain as well, but usually we're going to see the positive ion form. So generally we're going to see tin form a positive charge and not that negative charge. But instead of being 2 electrons away, it is 4 electrons away. From a full shell. So now that we've identified the difference, we can make a prediction using our rules. Which one would we predict would be more reactive? Well, we said elements that are closer to a full valence shell are more reactive, which means we would predict that strontium would react more violently or readily. Because it is closer to a full shell. Tin, farther away from a full shell. So is it going to react? Eventually. Is it going to react as easily or as quickly? No. We would say strontium is likely to be more reactive. We can also check to see if this fits the trend. So we identified our reactivity for metals as having an extreme towards the lower left-hand corner of the table. Strontium, very close to the left side. Tin, not as far to the left. So strontium also fits our trend. Strontium is closer to the left-hand side of the table, which is where our more reactive metals are going to be. Notice I said metals. This reactivity trend is only for the metals. If we were looking at non-metals, we would see some things be reversed here. All right, so that's example 1. We can follow rules and predict reactivity, and we can explain why a little bit. Now, example 1, we were looking at 2 elements in the same row. So we practice some row logic. For example 2, we're going to flip that. we're going to look at two elements in the same column. So we're going to predict reactivity for beryllium, should spell that right, versus calcium. And we're going to ask ourselves the same question. Which would we expect to be more reactive and why? Okay, so finding them on the table. Beryllium, little tiny beryllium. Calcium, little bit bigger, but still something that we can manage and draw. Now, here, the Lewis dot structures are not going to help us. In order to predict differences in reactivity, sorry, in order to predict differences in reactivity, we need to look at differences in electron structure. They both have two valence electrons, so we can't be comparative there. However, if we were to go back to the Bohr models, we are going to see some significant differences. Beryllium is going to have a fairly small Bohr model. It's element number 4. Mass is 9, so 4 protons, 5 neutrons, which means I only need to place 2 electrons in the first ring and then 2 more in that second ring. When we draw calcium, I'm going to have a much bigger model. When we draw calcium, I'm going to have 20 protons in my nucleus and 20 neutrons. And instead of 2 rings, I'm going to have 4. And instead of placing 4 little electrons, I've got to place 20. 2 in the first ring, 8 in the second ring, 8 in the third ring. And then 2 in that fourth ring. Now, the electrons we care the most about for both examples are going to be our valence electrons. So I'm going to highlight those or go around those in yellow. Those are our focal points. And when these elements go to lose electrons, go to form ions and react, they're going to do the same thing. They're both going to get rid of 2. However, we can use the trend I already gave you to predict who's going to give those away a little bit easier. So if we look at our extreme for reactivity, We said elements are more reactive towards the left. We also said elements, specifically metals, are more reactive towards the bottom as we get more rings. Well, who has more rings here? Calcium. So calcium here is going to be our more reactive element. And it's due to the distance between the nucleus and the valence shell. The nucleus is essentially a magnet. That magnet holds on to electrons. If we imagine each shell is a mile, calcium is trying to hold on to electrons that are 4 miles away. Beryllium is holding on to electrons that are 2 miles away. They're closer. These electrons are farther away. From the nucleus's magnetic pull. Since they're farther away, those electrons are going to be easier to pluck off. Which means we can predict that calcium is going to react more readily. So that's what we're going to be looking at in this unit. We're going to be looking at comparing elements and using trends to identify different traits for pairs of elements. Now, if this still feels a little tricky, that's okay. It's our first day. It's our first lab here. But you've got the idea. What are we doing? We're comparing elements. Using trends we've been provided, we can predict different traits for those element pairs. If calcium is going to be our more reactive element, we can predict that beryllium is going to be our less reactive element. Even though both elements are going to have the same outcome. They're both going to form ions. I'm not going to draw the whole Bohr model again. They're both going to form +2 ions, but calcium's going to form that ion more readily, which means it's going to be more reactive than another example in its column, say beryllium.